Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss interpolating polynomials. So in this topic, we will see how to find interpolating linear and quadratic polynomials. We will learn about the Vandermonde matrix and see how to interpolate endpoints with a polynomial of degree n-1. We will review why it is necessary to use partial pivoting when solving systems of linear equations. We will also see how to decrease the error in interpolating polynomials by shifting the x values before we find the interpolating polynomial. Finally, we will look at implementations of functions for finding interpolating quadratic polynomials in both C++ and MATLAB. Now suppose we start with 2 points, x1, y1, and x2, y2, and assume that the two x values are different. From secondary school, you can find the straight line that passes through these points. So what you would have done is assume the line is of the form y is equal to mx plus b. You would then substitute both pairs of points into this equation. That would give a system of two equations in the two unknowns m and b. Now, you'd probably then subtract equation 1 from equation 2 to get y2 minus y1 equals mx2 minus mx1. You can now isolate m, and this gives m being the ratio of y2 minus y1 over x2 minus x1. Substituting m back into the first equation and solving for b gives us that b is equal to y1 minus this slope times x1. All right, so since this is a system of two linear equations, we can rewrite this as a problem in vector spaces. So here we have the matrix x11, x21 times the unknown vector mb, and that's equaling the target vector y1, y2. All right, now one very important question is, many students will ask, why is there that second column of ones? This is because it is the unknown m times x1 that gives us the x1 in the entry 1, 1, but then it's plus b times 1 equaling y1. So the unknown b is multiplied by the constant 1. Therefore, that last column is always going to be a column of ones when we're doing any form of linear interpolation, at least polynomial interpolation. So, for example, suppose we want to interpolate these 2 points. Well, in MATLAB, we can set up the matrix as follows and solve the system of linear equations using the backslash operator. This gives us the solution to 4.2. Now remember, the first column is associated with the slope m. The second column is associated with the constant b. So the first answer in the solution is m equals 2. The second one is b is equal to 4.2. Thus, the interpolating straight line is y is equal to 2x plus 4.2. However, given 3 points x1, y1, x2, y2, and x3, y3, with all three x values being different, can you find a straight line passing through them? Well, of course not. After all, here we have an example. The first point is negative 1, 1. The second point is 1, 1. And the third point is 2, 4. Now, the straight line y equals 1 passes through the first 2 points, but not through the third. And as you may suspect, there's no straight line passing through these 3 points. However, there is a quadratic that passes through these 3 points, y equals x squared. And that, again, should be reasonably obvious from secondary school. Now, given 3 points, with all 3 x values being different, can you find a quadratic passing through them? Well, suppose the quadratic is of the form ax squared plus bx plus c. If this quadratic is to pass through each of these 3 points, then for each of these points we should be able to substitute in the x sub k, and the result should be y sub k for k equaling 1, 2, and 3. All right, now remember that x1, x2, and x3 are all given. Therefore, they are constants. Therefore, this is nothing more than, again, a system of 3 linear equations in 3 unknowns with the matrix we see here, the unknown vector a, b, and c, and the target vector of the y values. Now, from here on in this course, we will always write down unknown polynomials in the form a sub 2 x squared plus a sub 1 times x plus a naught. The justification here is that the subscript on the coefficient equals the exponent of the term. This is a lot easier than other representations. So now a sub 7 is always the subscript of x to the 7. A sub 4 is the subscript of x to the 4. Thus, if we were to represent our previous problem in light of this representation, we would be solving this system of linear equations. Now, does this system of 3 equations in 3 unknowns have a unique solution? You'll recall from your course in linear algebra, there is either one unique solution, no solutions, or infinitely many solutions. Now, if the determinant of the matrix A is something that is non-zero, then there is one unique solution. If the determinant is 0, there is either infinitely many solutions or no solutions. Well, in this case, we can calculate the determinant, and if you calculate it out and simplify, you will find that the determinant is equal to the product of the differences of the 3 different x values. Now, if all 3 x values are different, then the determinant, the differences of each pair, are non-zero, and the product of 3 non-zero numbers is a non-zero number. So as long as all 3 x values are different, a unique solution exists. If, however, any 2 or even all 3 of the x values are equal, the determinant is 0, and consequently there will either be no solutions or infinitely many solutions. Let's do an example. Find the interpolating quadratic polynomial that passes through the 3 points 0.4, 3.12, 1.2, 3.28, and 3.5, 18. To solve this, we must solve the following system of 3 linear equations in 3 unknowns. And again, the third column is all ones because the third unknown, a naught, is the constant coefficient. So the x values make up the matrix, the y values make up the target vector. Now in MATLAB we would do the following. we could assign a matrix V, the following matrix, which are the x values either squared or by themselves, or the last column of ones. You would then solve the system of linear equations by using the backslash operator, and that gives us the vector 2, -3, 4. Again, the first column is associated with x squared, so the first coefficient, 2, is the coefficient of x squared. The next column is associated with x, and therefore -3 is the coefficient of x, and the constant coefficient is 4. So the interpolating quadratic that passes through the three given points is y is equal to 2x squared minus 3x plus 4, and you're welcome to plug those numbers in to see that that is indeed correct. Now, writing down these matrices in MATLAB can be error-prone, and also tedious and slow as well. The Vander function in MATLAB generates this matrix for you. Consequently, instead of writing this matrix for these three x values, 0.4, 1.2, and 3.5, which gives us this matrix here, we can instead call Vander with a vector with three entries in it, 0.4, 1.2, 3.5, the three x values. As you can see, this gives us exactly that same matrix. This matrix is actually called the Vandermonde matrix. Now remember, however, that just because the determinant of a matrix is non-zero, this does not mean we can find the solution numerically, at least not to significant precision. So suppose the 3 points instead were 0, 0.001, and 100. So this is the Vandermonde matrix. We can create this matrix in MATLAB as follows. Those are the three x values, and that is the corresponding Vandermonde matrix. I've cleaned up the output a little bit just so that you can see more clearly what's going on. Now the determinant of this matrix, if you were to calculate it out, is exactly negative 9.9999. So clearly non-zero. After all, the three x values also are different from each other. However, the condition number of this matrix is 14 million. Remember that the condition number tells us how much any error is going to be magnified to a maximum. So any numerical round-off error is going to result in an amplification of that error by up to a factor of 14 million. If there is any error in the y values, even 0.01% relative error, that error will be magnified by a factor of up to 14 million. Consequently, this is probably not a good choice of x values. Fortunately, equally spaced numbers, or x values, tends to result in a matrix that has a smaller condition number. So if our x values were 0, 1, and 2, equally spaced, then the condition number of the Vandermonde matrix is about 13.9. Let's shift the middle x value down to 0.9. So shift it to the left by 10% of the difference. Now the Vandermonde, the condition number goes up to 14.1. If we shift the middle point over to the right by 0.1, again the Vandermonde, the condition number goes up by a little bit. Not only that, if we shift all of the numbers to be around 0, so equally spaced but -1, 0, 1, the condition number drops to 3.2. So a judicious choice of x values is actually appropriate. Now, fortunately, most engineering data comes from periodically sampled sensors. What this means is that by default, the x values are going to be equally spaced. Now, actually, they're t values rather than x values because they are samples in time. It is the y values that are the values of the samples, whereas the x values, or more correctly t values, are the points in time at which the samples are taken. Now let's generalize the previous result. Here's a theorem. Given n points, x1, y1 through xn, yn, with all the x values being distinct or unique, then there exists a unique polynomial of degree n minus 1 that passes through all n points. Proof. Well, this is actually a constructive proof. The system of linear equations for that polynomial of degree n minus 1 passing through those n points is the system of linear equations shown here. Now, normally one cannot use the determinant numerically to determine if a matrix is invertible. However, this is an algebraic matrix, and thus it is possible to use deduction to deduce that the determinant of the matrix, the Vandermonde matrix, is this product of products. In fact, what it is it's actually the product of all possible pairwise differences of the many different x values. If all the x values are different, all the differences are non-zero, and therefore the product of a whole bunch of non-zero values is going to be non-zero, and thus a unique solution exists. So as long as all the x values are different, given n points, there exists a polynomial of degree n minus 1 that passes exactly through all n points. Once again, having n points where the x values are equally spaced tends to have smaller condition numbers. Now, equally spaced x values are not actually the ideal case, but the ideal points are beyond the scope of this course. And as mentioned before, these points are usually coming from a sensor being periodically sampled, and thus the x values, or more correctly the t values, will be equally spaced. So, for example, here we have the x values 1, 2, 3, 4, equally spaced. The condition number, it's actually quite large, it's about 1,000. If I now instead shift the values to 1, 1.1, 3.9, and 4, the condition number increases. And the closer the two middle points come to the endpoints, the larger the condition number will be. Now, if all we do is shift the values over, so equally spaced, but now the x values are -1.5, -0.5, 0.5, and 1.5. So again, we just shifted the values 1, 2, 3, 4 over by -2.5. We now get a condition number that's significantly smaller, 9. So significantly smaller by 2 orders of magnitude. Also, there are more ideal numbers. if we shift the interior x values around, we can get a slightly smaller condition number. All right, what's the takeaway here? Do you have to know where all of these come from or know how to calculate these? No, you do not. Instead, what you must understand is, first, equally spaced x values are actually reasonably good. Also, x values that are closer to the origin tend to be better than x values like, say, 100, 101, 102, and 103. We are going to use these facts in the next few slides. Now, in the previous topic on linear algebra, recall that we discussed how using simple Gaussian elimination and backward substitution with floating point numbers may lead to errors, and so instead we introduced Gaussian elimination with partial pivoting. Well, we can actually see the problem right here. Suppose we want to interpolate these 2 points, a very small number, 4.545, and 2.523 and 5.237. We must therefore solve the following system of 2 linear equations in 2 unknowns. Now, if we were to use our 6-digit floating point representation we introduced previously, then if we simply used Gaussian elimination without the partial pivoting, the solution we find is the constant polynomial y is equal to 4.545. As you can see, this passes through the first point, but it does not pass through the second point. However, if we do use partial pivoting, then we do get 4 digits of precision, giving us the polynomial y is equal to 0.2743x plus 4.545, which is as close as you can get to passing through these 2 points. So this is the solution we are indeed looking for. Now you may be wondering, why would anyone want to interpolate such 2 numbers instead of just having the first number being 0? Well, once again, floating point round-off error comes to the rescue. Here's a C++ program. The first point is to set the precision for the output to be 16 decimal digits. Now, here we have a for loop. The for loop is going to run from -1 up until x is greater than or equal to 0.05. And with each step, we will increment x by 0.1. We may be sampling 10 times a second, or if you have film, it may be 24 samples per second. Or if you are counting per minutes, you may have 60 samples or even 600 samples per minute. Nevertheless, let us print out the x values just by starting at -1, then going to -0.9, -0.8, -0.7, and so on and so forth. Well, as you can see, after adding 0.1 onto -1 10 times, we don't get 0, we get an exceptionally small number. So this may indeed be a number that could be fed to solving a system of linear equations. And if you were to do this, then you would, if you did not use partial pivoting, get the wrong answer. So we can even see this issue in MATLAB. That very small number we got by adding 0.1 to -1 10 times is actually 2 to the -53 plus 2 to the -55. From this, you should even be able to deduce the binary representation of this number. Now, in MATLAB, we can solve this system of linear equations. And we get that the polynomial passing through these points is the one we see here, 0.27428 x plus 4.545. Suppose instead we create the augmented matrix and then we add an appropriate multiple of one row onto the second. Oh dear, those are huge numbers in the second row now. 1.818 times 10 to the 16. We can now solve for the constant coefficient by using backward substitution and substituting that value back into equation 1. We can now solve for the slope, but the slope is now 0, not 0.27428. So once again, we can see that MATLAB does use reasonable means to approximate or solve a system of linear equations with the backslash operator. Once again, you don't have to understand all these mechanisms. You just have to understand that simply applying linear algebra will result in wrong answers once in a while if you're not careful about avoiding issues with using floating point numbers. All right, recall that another issue we had is that the condition number of the Vandermonde matrix tends to be smaller if the x values are smaller. Suppose we start with wanting to interpolate these 3 points, where x1 is less than x2 and x2 is less than x3. Now, we could find the interpolating polynomial that passes through these 3 points, but let's move these 3 points closer to the origin. Let us subtract x2 from each of the x values. So the first x value is now x1 minus x2, the second x value is 0, and the third x value is x3 minus x2. Doesn't seem to make much difference. However, now if we wanted to evaluate the original polynomial at some value of x between x1 and x3, we would find the interpolating polynomial between the next set or the new set of 3 points, and then we would evaluate that new interpolating polynomial at those new points at the value x minus x2. All right, so the Vandermonde matrix of the original 3 points is on the left. The Vandermonde matrix of the new 3 points, where each of the x values are shifted to the left by x2, is the matrix we see here. Consequently, at this point, we are solving this system of linear equations to find the interpolating polynomial that goes between the y values y1 through y2, y3, with the x values x1 minus x2, 0, and x3 minus x2. Now, from this system of linear equations, we may immediately deduce that the constant coefficient is y2. So we don't even have to worry about it anymore. We're actually simply solving this system of 2 linear equations and 2 unknowns, because A0 is y2. Therefore, to recap, Suppose we want to find the interpolating quadratic polynomial that passes through these 3 points. The x values are unique and in order. Instead, we will find the interpolating polynomial that passes through these 3 points. This requires us to find this particular quadratic polynomial. This requires us to solve the system of 2 linear equations in 2 unknowns. And having found the polynomial p, if we want to evaluate that interpolating polynomial p at some point x between x1 and x3, we actually evaluate the polynomial p at x minus x2. Now, remember also that I pointed out that engineers tend to sample points equally in time. Therefore, the x values may be equally spaced by some value h. Consequently, the x values x1, x2, x3 may actually be x2 minus h, x2, and x2 plus h. So to find the interpolating quadratic that passes through these 3 points, instead we will find the interpolating quadratic that passes through those 3 points. Solving this requires us to solve this system of 2 linear equations in 2 unknowns. This is something that you can actually solve yourself algebraically. If you were to do so, you would find that the constant coefficient is, once again, y2. The coefficient of x squared is y3 minus 2y2 plus y1 all over 2h squared, and the coefficient of x is just y3 minus y1 over 2h, which, as you can see, is simply a slope. All right. This now gives us a quadratic that passes through the second set of 3 points, and if we wanted to evaluate the polynomial that passes through the first 3 points, let's say x is some value between x2 minus h and x2 plus h, we would evaluate this second interpolating quadratic at the point x minus x2. We can even implement this in C++. Here, the first argument is x2 and the second argument is h. So the 3 points are x2 minus h, x2, and x2 plus h. The 3 y values are passed as an array of 3 values. Now we would like to find the interpolating quadratic that passes through these 3 points and evaluate it at the point x. Well, we can calculate the coefficient a1, we can calculate the coefficient a2, and then we can evaluate the polynomial at the point x minus x2. We can also implement this in MATLAB. Once again, MATLAB is not typed, and so therefore you should pass the correct values, including the correct types. And remember that accessing entries of a vector in MATLAB has indices going from 1 to n, not 0 to n minus 1, and parentheses are used, not brackets. But as you can see, a lot of it is the same, and the returned value y is whatever value y has when this function exits. Let's take a look at this example. Here we are trying to find an interpolating polynomial that passes through these 3 points. All right, so we'd like to find this interpolating polynomial, and we'd like to evaluate it at the point x is equal to 1000.04. This is exactly the value y is equal to 0.864. And again, I chose the y values specifically to give us this reasonably clear and exact answer. Thus, we can solve the system of linear equations given by this matrix, or we can use the technique we just described, finding the interpolating quadratic that passes through these three shifted values, shifted only in the x value, and find the interpolating quadratic that passes through those 3 points, and then evaluating this interpolating quadratic not at 1000.04, but rather at 0.04. Let's try both. All right, so in MATLAB, we could create the Vandermonde matrix from the original 3 points and solve that system of linear equations with a target vector with the 3 y values, which gives us these coefficients of the quadratic polynomial. We could then evaluate this quadratic polynomial at the point 1000.04. All right, the correct answer was 0.864. We're pretty close, but let's try calling that quadratic interpolation function that used the other approach. Oh dear. Yeah, it's 0.864, but there's much more precision in that answer. The answer is more accurate. In fact, the relative error with the first technique is 44,000 times larger. That's more than 4 orders of magnitude larger. All right, so if this is just one simple case, imagine if you were doing this repeatedly. And once again, if these values were then being fed back to other systems of linear equations, which then have additional errors introduced, again, with some very simple techniques, we were able to reduce the relative error by 4 orders of magnitude. This is the approach we will be taking throughout this class, using our understanding of numerics, linear algebra, to have reasonably numerically stable solutions or approximations to problems we are trying to solve. In this case, finding and evaluating interpolating polynomials. You'll recall that the condition number tells you how much an error may be magnified. In this case, the only error we're worried about, or the only cause of error, is the numeric round-off error when we are calculating the results. With the original 3 points, the condition number is 212 trillion. This means any numeric error may be magnified by up to a relative amount of 212 trillion times larger. When we shifted it towards 0, we were solving this Vandermonde matrix, which resulted in a numeric or a condition number of 10. So the first one has a larger condition number by 21 trillion, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, over 14 orders of magnitude. Now, some other issues about interpolating polynomials. First of all, higher order interpolating polynomials result in higher errors. The interpolating polynomials are more sensitive to initial error in either the x values or the y values, and the intermediate error is also larger. Consequently, we will be restricting ourselves to low-degree interpolating polynomials: quadratic, cubic, perhaps quartic. Second, if we are interpolating a number of x values where x1 is the smallest and xn is the largest, it is generally only a good idea to evaluate the interpolating polynomials for values of x between the smallest and the largest values, hence the term interpolation. If we are evaluating the interpolating polynomial for values that are either less than the smallest x value or the largest x value, this is called extrapolation. And at these points, the error tends to increase much more rapidly. After all, the error of a interpolating polynomial can be described as being a product or a scalar multiple of the product of x minus xk for each of the k's. So once we get outside the interval, that tends to skyrocket. Incidentally, here's a small improvement to our program we could make. What we could do is map the values x2 minus h, x2 and x2 plus h not to negative h0 plus h, but rather map them to negative 1, 0, 1. So essentially subtract off x2 and divide by h. This produces a program that has even fewer floating point operations and thus further reduces the introduction of round-off error. Now, the problem with the previous implementation is that whenever we want to evaluate the interpolating polynomial at a point, we must recalculate the coefficients. So it makes a lot more sense to turn this interpolating polynomial function into an object. So here we have a quadratic interpolating polynomial. We have two public member functions, one for generating it and then another one for evaluating it. Consequently, the constructor calculates all of the coefficients and saves the relevant information. Consequently, the eval member function only needs to access the previously calculated and stored coefficients, thus once again making this significantly more efficient. Following this topic, you now understand how to find interpolating polynomials using linear algebra. What we do is we create the Vandermonde matrix and then we solve a system of linear equations to find the coefficients of the polynomial. You also understand why the last column of the Vandermonde matrix is all ones, because that is the multiplier of the constant coefficient. We've revisited the justification for using partial pivoting with Gaussian elimination, where we have seen where a very small x value could result in catastrophic errors if we do not perform partial pivoting. We also have seen, and you understand, that if we have very large x values in the Vandermonde matrix, this can significantly increase the error, as seen in the condition number, and this consequently suggests we should be shifting the x values closer to the origin. You are aware of some further issues with interpolating polynomials. We do not want to, for example, calculate interpolating polynomials that are too large. They are very subject to error. And we do not want to use extrapolation, at least not too much with interpolating polynomials. Finally, we saw some brief but simple improvements to our interpolating functions, including the idea of creating a class so that we do not have to continually calculate the coefficients. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!